I want to pick M, a big Cohn-Macaulay module. So this is where the commutative algebra comes in. Deep results from commutative algebra come in. The existence of big Cohn-Macaulay modules. So there exists, what this means is that there exists a sequence x, x1 to xs plus 1. So the indices get a little bit annoying, but that's how it is, where s plus 1 is the dimension of R. I want to match this s with that. So you have a sequence of s plus 1 elements which are regular. M regular. And the other property, of course, is that of a big Cohn-Macaulay module is that it's not divisible. M times M is not M. All right. So pick a big Cohn-Macaulay module and a sequence which is regular on it. And now let set xn to be the check complex on x1 to xn plus 1 tensored with n. Well, what do I mean by this? So recall that this check complex, this is what computes local cohomology. We'll hear more about this in the next lecture, I guess. But this is, one way to think about it is, this is the complex and this is the check complex on one element x1. So the check complex on the sequence is obtained by tensoring the one for each and with m. Yeah. So this computes local cohomology of m with coefficients with respect to the ideal generated by x1 to xn plus 1. Okay, and there are natural morphisms. From xn to xn minus 1. So the cohomology with n plus 1 elements is smaller than the cohomology with n minus n elements. That's what's going on. Right? Okay. So in fact what you get is a sequence xn. No. Well, the last one is xs. So we get a picture like this. So for x, the highest value for s, n is s, because there are s plus 1 elements. So we have xs, xs minus 1, vs, vs minus 1, etc. Then we have x naught, which is the check complex on one element x1. And finally, we also have the check complex on the empty set, which gives you m. Okay. All right. So this is the sequence down there, and I have to test that this f violates the conditions of the Gauss lemma. So the first claim is that these are all Gauss. And right, we have to check that these morphisms are all Gauss of complexes. So why is this? Well, the check complex, as I said, computes local cohomology, and local cohomology is depth sensitive. So if you look at, so here's an argument. If you look at the cohomology of this complex, so this is the, so let me look at the complex xn. So this is in degree, the natural degree here is the upper degree. Yeah, so let me write it like this. So if you look in degree j, So as I said, this complex computes local cohomology. So this is the local cohomology in degree j on the elements x1 to xn plus 1 with coefficients in m. All right? That's what it is. Now, because this is a regular sequence on M, this cohomology modules, this is 0 for j, not equal to n plus 1, and non-zero otherwise. But that the main point is that it's the only possible non-zero cohomology is in degree n plus 1. All right? So this so the complex xn has homology only in degree n plus 1. Now if you look at the map between two, this one has homology in degree, for example, s minus 1. The next one will have homology only in degree s minus 2. So it must be 0. It's 0 for trivial reasons, for degree reasons. Each complex has cohomology in 1 degree and the degrees are staggered. Yeah? So therefore these are goes. Okay, so this explains this claim. Now the next part is a little, so what do we have to check? So I'll leave this here. So the next claim we have to check that I do have the ghost lemma here. So we have to check that h of this map is non-zero. So let's see what's going on here. So we have h of xs box tensor f going to x naught, which is m, box tensor f, right? So we want to check that this map is non-zero, the composite map. We have a sequence of goes, and if I tell you that this map is non-zero, then this lemma would be violated. This lemma would imply that the class must be at least S. So I must have made a mistake here. This must be for strictly less than S. Class 0, no, that's okay. That's okay. What if this is non-zero? This would imply that the class of f is at least S plus 1. It can't be S, because if the class is at most S, then this map should be 0. But I'm going to explain why it's non-zero. So this would imply the class is at least S plus 1, but S plus 1 is the dimension of the way I've chosen S. Okay, so why is this non-zero? Well, so remember the hypothesis. We had, where was the reduction? So we had this retract, a direct summand of f, which is d. So because it's a direct summand, this homology would be a direct summand of that, because this d is a direct summand of f. So this homology is a direct summand of that. So it's there's certainly a surjection here, and then we have m tensor d coming down here, and then we have this natural map. So we have a commutative diagram like this. You want to check this as non-zero. It's enough to check that this one is non-zero, this composite.